Time for us to do some problems involving polar sketching and also talking about tangent lines to polar curves. As always, it's good to do problems. It might seem like problems are not something we want to have, but in math, problems are a wonderful thing to have because problems are the way that we grow. And we grow by doing problems and more challenging and more interesting. So do as many as you can. If you're following along with the video, make use of the pause button. See a problem that you like, one that'll help you grow? Try it out on your own first. And then if you do need me, I'm here. Just unpause me, and I'll come along and give you a hand. Well, let's begin. Our first problem. Sketch the region where r is between 1 and 2 sine 2 theta. Okay, well, let's see, how would we begin? Let's start by thinking about what these curves are. So, let's start with r equals 1. That's pretty straightforward. What is that? Well, r is our distance from the center. And so r equals 1 says we want to have all the points which are distance 1 from the center. It means it's a circle. So there's r equals 1. All right, cool. Now, what about r equals 2 sine 2 theta? That one's a little bit more interesting. So let's think about what would happen here. So we're going to sketch our plane here. We'll come and fill this in a moment. But let's see, what can we do? Well, if we're not sure what to do in polar, what we can start by doing is say, well, let's do a little side note and say, suppose we just thought about how does this look as r as a function of theta. So this is not the polar curve yet. This is just saying, how does r behave as a function of theta? Now, the sine 2 theta just says, instead of repeating every 2 pi, we're actually going to squeeze things in so it repeats every pi. So we're just compressing by a factor of 2 our domain. The 2 on the outside, this 2 right here, this 2 sine 2 theta, is a vertical stretch. So the effect is it goes up and down, but instead of doing 1 period, it does 2. So if here's 0, here's 2 pi. Well, you mark some important points. Pi, pi over 2, 3 pi over 2, that's when we're going to hit the axes. And of course, the other important points are the points which are far away. That would include pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. All right, so what to do now? Well, since we know when we're hitting the origin, r equals 0, let's mark those. Now, the way I like to mark them is just say, okay, I'm going to draw rays corresponding to those angles. So you have r equals 0, of course, they happen to be the axes. R equals pi over 2, r equals pi, r equals 3 pi over 2. Okay, so that's going to tell me that I'm coming in as I hit those angles. So I'm coming in and out of the origin at those angles. And now I just figure out where am I going relative to those. So here it says, look, from 0 to pi halves, at 0 I come out of the origin all the way up to the point where I'm 2 away at pi over 4, and then I go back to the origin at pi over 2. So I'm going to do that. Out at 0, all the way out, back in. Now, from pi over 2 to pi, that's this upper quadrant up here. Pi over 2 to pi. So pi over 2 to pi, okay? This part right here. Except r is negative here. You see, we're below the axis. So normally we would be coming out into here, but since r is negative, we're going to go into the opposite part. So we're going to do what? Well, that says we're really going to come out here and loop and come back. So this is the 0 to pi over 2, then from pi over 2 to pi over here. And now, from pi to 3 pi over 2, so that's this piece over here. Pi to 3 pi over 2, we're coming out and coming back in. And, okay, my picture's not the best, but, you know, they should all be roughly the same shape. All right. And finally, from 3 pi over 2 to 2 pi, normally would be here, but r is negative, so it ends up back over here, and so it's going to come out and back in. So, there we go. There's our shape, roughly speaking. Like I said, my picture's not the best. That's all right. It doesn't have to be a perfect picture. Now, what do we do? Well, we can combine them. And we say, perfect. When we combine these, what do we see? Well, what we see is the following. We see our circle of radius 1, and then we see kind of almost like you might describe it as a butterfly. And so it does the following. It loops 4 times, right? It comes out and back in, then it comes down, out, back in, then it goes out, back in, then it goes out and back in. All right. Now, we've drawn the 2 curves. And at this point, you're probably like, easy. I have to be outside of the 1. Okay, so I have to be outside of that circle, but I have to be inside this curve. And so we say that's got to be the following, right? Outside of that circle, inside of the curve. That sounds like a good answer. Sounds like a great answer. I'm even drawing it here. So, is it the right answer? No, it's not the right answer. This is actually wrong. I shouldn't have drawn it. Okay, what? Now, at this point, you're probably saying, but it looks so good. I'm outside the r equals 1 and I'm inside the other curve. How could it be wrong? Okay, so this is not correct. You've got to be careful here. Now, let's actually come back and use this picture. This picture will actually reveal why we're wrong, and will also show us how to make ourselves right. Now, what can we do? Well, what we can do is by looking at this, we say, this is the r equals 2 sine 2 theta. We can also, in the same picture, sketch r equals 1. And now we can say, okay, well, where is it the case that we're above 1 and below 2 sine 2 theta? Well, it happens twice. In that first bump and in that second bump. So there should only be 2 little pieces and not 4 little pieces. Okay, so what is the right picture? Well, the curves were right. The curves were right. So we'll get a chance to draw it again. We'll get good at drawing these. All right, so we draw our curve with a circle. All right, that's not so bad. And then we have our 2 sine 2 theta. And remember, it's coming out and back in every quadrant. And as we draw this, the key is that even though it looks like all these 4 are the same, remember, every other one, r is positive, and then every other one, r is negative. And only the positive ones are we going to have it be the case that 1 is less than or equal to 2 sine 2 theta. See, if 2 sine 2 theta is negative, it can't work at all. So, which are the right ones to shade? Where do we actually end up at? Well, the answer is we end up with the first one between 0 and pi halves. That's where r is positive. And in the third one, between pi and 3 pi halves. And there we go. That's the answer. Good. Good. All right. And, okay. Well, what's the moral? Be careful. Because sometimes we think in our mind, we forget, oh, R might be negative, R might not be negative. And we have to take that into account when we have these pictures, especially when things start looping through the center. Things can get very, very interesting. Again, and I'm not going to do the best job of demonstrating this, but I hope that you can start to see that there's actually this beautiful connection. Is even though this picture really isn't the polar curve, it stores so much about what's going on. So that as you read this from left to right, you can say, look, this motion here translates into this sort of pivoting through down here, so that you can translate back and forth between the two settings. And that ability to sort of intuit, okay, I know how to graph here, how do I translate into there? That's going to be a very important tool if we're trying to understand what's happening in polar curves. Well, all right, one problem down. Of course, we have more problems. Who'd have guessed? I think we all would have guessed by this point. So let's try another one. Sketch the curve r squared equals 4 sine 2 theta. Well, we actually are pretty close to doing that. We did that just a moment ago. And so let's just sort of think through our reasoning here. So first off, let's do the following. We'll have theta and r, and let's graph just 4 sine of 2 theta. Not worrying about r squared. So I'm just going to say, suppose this is what we were going to graph. R equals 4 sine 2 theta. Well, it's the sine function. The 2 theta on the inside squeezes it in. The 4 on the outside stretches it up and down. And so, as a consequence, what we have is it'll look something like this. Okay, there's 2 pi. So it's essentially we're instead of squeezing a single period into 0 to 2 pi, we're going to get 2 periods in between 0 and 2 pi. And the top here is at 4, and the bottom here is at negative 4. Now this is if we sketched r equals 4 sine 2 theta. But remember, what are we graphing? We're graphing r squared equals 4 sine 2 theta. So what we want to do is we want to take the square root of that. Now, what does that translate into? Well, that's the following. We could say, look, if r squared is 4 sine 2 theta, that says really r is plus or minus 2 square root sine 2 theta. Okay, well, what is that going to do for us? Well, if we think about it, one of the things that it says is that these parts down here are out, because that's where sine 2 theta is negative. I can't have a r squared equal a negative value. So what we get is we really get 2 possibilities. So if we mark here, we have 0 and pi halves, and then there's a pi and a 3 pi halves. So we have sort of 2 possibilities. One is we have the plus part. So that would be something that goes up to 2 and looks something like this. It's going to be the same basic shape, right? Because the square root, the larger the value, the larger the output. So if you go up and down, and we take the square root, you still go up and down. And again, we go up and we go down. Or we could be the negative, which means what? Well, we could go down and up, down and up. So those are our 2 possibilities. Those are our 2 curves that we might have. So what does the graph look like? Well, to see that, now we translate and say, okay, what's happening? Well, if we look at the angles that are interesting, where do we come into 0 or out of 0? Well, at 0 and pi halves, so 0, pi halves, and at pi and 3 pi halves. So, let's sketch our curves. First off, r equals the positive part, the top part here. So 2 square root sine 2 theta. Well, what happens? Well, it says here, between 0 and pi halves, you come out a little ways, and then you come back. We can even say that this is distance 2 away. So maybe we'll just do a little dot, 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 2. Just to emphasize we know how far away we are. And then nothing happens. Then from pi to 3 pi halves, okay, out and back in. And again, a distance of 2. Okay, and between 3 pi halves and 2 pi, nothing happens. All right, so there we go. But remember, r could have been the other part. R could have been negative, so we got to check what happens there. Okay, so what happens? Well, let's think about it. We're going from 0 to pi halves. If we're positive from 0 to pi halves, we're up in this quadrant. If r is negative, we shoot sort of to the opposite side, right? So that says we're going to actually be down here. So if we had been positive, we would do this loop. Since we're negative, we come out this loop. And that's what we get. You'll notice it's very similar, right, to what we did. Okay, now nothing happens. Now, pi to 3 pi halves, we're positive, we're out here. If we're negative, we go across, and we come over to here. So at pi, we would be coming out from this direction for positive value of r. For negative value of r, we're coming out this direction. So we come and we end up tracing over it. And therefore, that's the sketch. So what happens is kind of similar to before, but now, in the previous problem, we had loops over here. That was where our sign value was negative. And it said, look, it's not going to happen. We kind of have this sort of infinity symbol turned sideways. So there's the sketch of our curve. Kind of nice. Beautiful picture. Beautiful picture. All right. Well, let's do some more. Let's switch over and talk about some tangent lines. So, find the tangent lines, or rather it says lines tangent, same thing, to the polar curve, and r equals 2 plus 4 sine 2 theta at theta equals pi fourths and theta equals pi halves. And so we don't actually have to sketch it. They made a sketch for us. It's kind of interesting here. It looks almost like some of those pictures you see of supernova explosions. We have these big gas clouds. There's this little tiny thing on the middle. And all right, well, what do? Well, we can actually mark where we're going. It's not too hard to see. We see theta equals pi fourths. Says we're looking for that tangent line, whatever it might be. And pi halves looks like we're looking for that tangent line. Now you might say, are we sure we should go up? Well, yeah. When you plug in pi fourths and pi halves, you'll see that this value is greater than or equal to 0. So these really are the points. So we're looking for that tangent line and that tangent line. Now how do we find our tangent lines? Well, whenever we're looking for lines, you always look for two pieces of information. Point, slope. Very easy. Easy to do. Easy to keep track of. So we're after point and slope for these pieces. Well, to help us out, we should say, take our polar curve, translate it to parametric, because we know how to do things for parametric. So what do we have? x of theta, well, that's r. So I'm going to write down what r is, 2 plus 4 sine 2 theta times cosine theta. Y of theta, that's r, 2 plus 4 sine 2 theta times sine theta. So r cosine theta, r sine theta. All right, so that's how we do our conversion. Now that we have our curve in polar coordinates, our next thing to do is to sit down and say, all right, let's think about things like slope. How do you find the slope? Well, the slope is y prime of theta over x prime of theta. In other words, change in y over change in x. And this is the part I often make a mistake on. So I'm going out of my way to point out my mistakes so that I don't make that mistake. So what's the mistake I often do? Oh, see, I see we often write x first and y. So oftentimes, okay, take the derivative up the top and then derivative the bottom. No. See, gotta switch them. See, the derivative of y goes on the top, derivative of x goes on the bottom. So, derivative of y. How do you do it? Well, product rule. So, derivative of the first term. Well, that's 2 goes away. Derivative of 4 sine 2 theta will be 8 cosine 2 theta. And that's because derivative of sine is positive cosine, and chain rule, the 2 comes down, multiplies by the 4. So derivative of the first times the second plus the first times the derivative of the second. Well, that's cosine. Now, the denominator, take derivative of x. So derivative of the first, it's actually the same. We can just copy it from above. Times the second, now it's cosine. Plus the first, again, just copy it from above. Times the derivative of the second, which is negative sine. All right, and there we go. So that's going to give us our slope, and once we have that, we'll be in pretty good shape. So let's do our slopes. So we have our two values. So at pi over 4, well, what happens? We have a couple of things. If we double pi over 4, we get pi over 2. Cosine of pi over 2 is what? It's 0. Well, that's great. How about sine of pi over 2? It's 1. Beautiful. So this is going to be wonderful. So what we get, well, because there's going to be a 0 there, that's going to make that whole term 0. Plus, now here, we're going to get a 2 plus 4. So that's 6. And then cosine of pi over 4. Well, cosine of pi over 4 is root 2 over 2. Downstairs, the cosine of pi over 2 goes away, so the first term is 0. And here, the 2 plus 4 sine 2 theta, it's still 6. And sine of pi over 4, well, that's minus root 2 over 2 because of the minus sign. And now we see, well, look, they're the same upstairs and downstairs except for a sign change, so we get negative 1. That agrees with our picture. See, look at our picture. It looks like we're sort of maxing out as far away as possible at pi over 4. So it suggests this should be somehow perpendicular. So if I wanted to be perpendicular to coming out along pi over 4, I should have a slope of negative 1. And we do. Great. Good. Now, that's not the whole line. It's just the slope, but it'll help us get a good chunk of the way there. Now, let's do our other slope. Okay, so at theta equals pi over 2, what happens? Well, now we see this sine of 2 times pi over 2, sine of pi. That's going to go away. Okay, things are going to get interesting. All right, cosine of 2 pi is negative 1. Sorry, it's not cosine 2 pi, it's cosine 2 times pi over 2, so that's cosine pi. But that is negative 1, it should be negative 1. So we get 8 times negative 1, which is negative 8. Sine of of pi over 2 is 1. All right, plus, then we're going to have 2 plus 0, because sine of pi is 0. So that's 2. And cosine pi over 2 is 0. All right, divide by. All right, here we're still going to have negative 8 from the first term. Then cosine pi over 2, 0. So that term's going to go away. Plus, now here, 2 plus 0 again. All right, 2. You'll see the parts here, they copy. These parts are the same. Those parts are the same, which is great. It makes it easy. Same, same. Okay, now this minus sine pi over 2, well, that's a minus 1. So boom, boom, those are gone. Minus 8 over minus 2 makes it plus 4. Okay, so good. This is, our slope is 4. All right, well, that's a terrible looking 4. But there we go. Now we have our slopes of our two lines. All that's left is to find the points. So let's do that. All right, so let's start with, say, this point. That should be pretty easy. Well, what do we know? So at theta equals pi over 2, what is r? Well, r will be 2 plus 4 sine of pi. So r will be 2. In fact, we already computed it. It's this 2 that we saw over here. It's the same 2. So that says at theta equals pi over 2, which is going straight up, we go up 2 steps. So that tells us then we're going to go to the point 0, 2. All right, how about at theta equals pi over 4? Well, plug it in. Sine of 2 times pi over 4, sine of a half, that's 1. So it's really 2 plus 4, which is 6. It's the same 6 you see here. Not a coincidence. So you get r equals 6. Well, now, how do you get to your xy? Well, you do the same thing that you do here. Namely, x is r cosine theta, y is r sine theta. Cosine of pi over 4 and sine of pi over 4 both are equal to square root of 2 over 2. If you multiply by 6, you get rid of the 2. It goes into 6 with 3 root 2, 3 root 2. All right, great. Now we have our slopes and our points. Life is good. We can write down our answers. And so here we go. At theta equals pi over 4, we can say that y minus 3 root 2, our y value, is equal to our slope minus 1 times x minus our x value. So 3 root 2. Now we could, if we wanted to, write that as x plus y equals 6 root 2. That works as well. For theta equals pi over 2, what do we get? Well, we can actually see it really simple here, right? Because we have the y-intercept, we have the slope. So we can write in slope-intercept. Y equals our slope times x plus our intercept, which is 2. So there we go. There are the two lines. And we're done. We found it. Woohoo! All right. Well, just being patient and nothing surprising. We say, look, let's transform the problem to something we know. It's a great method. It works for math. It works for lots of things. Simplify to something you've solved before. All right, well, one more problem. Then we'll be done. So let's hope it's a good one. Here we go. Find all tangent lines to the polar curve r equals 4 minus 2 sine of a third theta, which intersects the positive y-axis. Wow, there's actually a lot going on here, so it's going to take us a little bit of time to digest everything. So let's think about what we can say. Well, first off, what's happening here? The 1/3 on the inside. See, we did a problems earlier where we said, oh, the 2 has a sort of compression. So instead of doing just one period from 0 to 2 pi, it does 2 periods. Well, what does the 1/3 do? It stretches it. So it means that in order to do one period, it has to go from 0 all the way out to 6 pi. In other words, we've got to go 3 times around before we're going to be able to reset. So what's happening here? Now, we don't actually have to know all the details, but I'm going to go ahead and tell you what happens. So what happens is the following. You start here, this is at 0, and you go through, and this will be loop 1. So at here we're at 2 pi. And then loop 2. And so that by the time we get here, this is at 4 pi, and then loop 3 again brings us back to 6 pi. So that's how the curve goes. It takes 3 loops around to reset. Now, what do we care about? Well, we care about the following. Namely, where do we hit the positive y-axis? And it looks like we hit it 3 times, 1 for each loop. Now, generally speaking, if we want to hit the positive y-axis, we say, well, what angle does it correspond to? And there's kind of 2 cases. So one case is if r is positive, well, what it means is you would have pi halves plus any multiple of pi. Because that says you want to look at pi halves and then you want to move forward. Okay, so examples of this are things for, well, pi halves. And then if you add 2 pi, that would be 5 pi halves or 9 pi halves and so forth. Now, the other thing that could happen, and we should just look at it, is what happens if r is negative? Well, in that case, you'd say, look in the wrong direction, opposite direction. But why? Because if you look in the opposite direction, but you back up, you end up going onto the positive y-axis. So in other words, if I'm looking down this way, but back it up, doot, 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 I end up on the positive y-axis. So this would be things such as 3 pi halves, 7 pi halves, 11 pi halves, and so forth. Now, which ones do we care about? In essence, we have to ask ourselves the question, what's happening to our r values? Can we say anything about them? Well, when we take a look at our r values, we see, well, it's 4 minus 2 sine of 1/3 theta. Now, the good news is sine is well behaved in the following sense. There's many senses where it's well behaved. Where it's well behaved in the sense that when you look at the sine, it oscillates up and down, up and down. It never gets very large, it never gets very small, just up and down all the way. So where does it go between? Well, it goes between -1 and 1. So that tells us, look, the smallest this can ever be is 2. And the largest this could ever be is 6. 2 would be when the sine of 1/3 theta is 1. 6 if sine of 1/3 theta equals -1. In particular, it says, look, this curve, whatever it's doing as it's doing its loops, it'll never get closer than 2 away from the center. And it will never get further than 6 away from the center. And in particular, r is always positive. So, since we know we have to go around 3 times, we know r is always positive, that tells us there are 3 values for theta we need to focus on. So these are our 3 values for theta. Okay, good. Now we know where we need to take our tangent lines. We also know we're on the positive y-axis. That helps a lot, because if we're on the positive y-axis, well, that says it's really easy to find the coordinates. You just have to know how far up do you go. Once you know r, life is good. Okay, so let's think about our points. So if we're doing our points, well, we have for theta equals pi halves, what happens? Well, we have sine of 1/3 times pi halves. That's sine of pi 6. What is sine of pi 6? Do you remember? It's a half. Now, how do you remember it? Well, I don't know. I mean, there's lots of ways. Let me grab a piece of paper here. And here's one way that I saw. And I didn't come up with this, but when I saw it, I thought, wow, this is cool. This is cool. So here, if you've seen this before, go ahead and skip a couple minutes. But what can you say? Look, there's an angle, and here's the sine of the angle. Now, oftentimes we write down our important angles: 0, pi 6, and there's pi 4ths, and pi 3rds, and pi halves. So those are sort of the important angles that we key off of. And we say, well, the values are 0, 1/2, √2/2, √3/2, and 1. And it's true, those are the right values. But somehow they're not the easiest to remember. But now, here's something that you can do. And you say, look, another way to write this is 0 is square root of 0 over 2. And 1 is square root of 1 over 2. Square root of 2 over 2 is square root of 2 over 2. Square root of 3 over 2 is square root of 3 over 2. And 1 is the square root of 4 over 2. So it has this beautiful, nice increasing pattern. Square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. How about cosine? Well, it turns out cosine is very similar, except it just goes the opposite way. Square root of 4 over 2, square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, and square root of 0 over 2. And there you go. There you go. And that's a nice little chart. It can help you remember if you're getting stuck. All right, so, but the moral is we have sine of pi 6 is a half. So then we have 2 times a half is 1. 4 minus 2 is, 4 minus 2 times a half, 4 minus 1 is 3. So that says r equals 3. So theta equals pi halves. You get r equals 3, which is just another way of saying the point is 0, 3, because it goes straight up the y-axis. How about 5 pi halves? Well, at 5 pi halves, what do you get? Well, you're going to get sine of 5 pi 6. Well, how does that work? Well, it's not in the chart. What you do is you think of the symmetry. So, for instance, you start with the circle, and you say pi 6 would be this angle here. This is pi 6. 5 pi 6 is if you came off in the other direction by the same amount. So it's like pi, go back pi 6. The important thing is the y values are the same. And the y values correspond to the sine values. So sine of pi 6 is the same as sine of pi 6. It's a half. So again, it's 4 minus 2 times a half. Still r equals 3. So that's still the point 0, 3. By the way, it matches our picture. You see, the first time through, we match with the second time through. So they were colliding there. Okay, well that leaves us with one more value for theta, and that's theta equals 9 pi halves. Well, 1/3 times 9 pi halves is going to be 3 pi halves. Sine of 3 pi halves, well that's sine if you go straight down. And that has a y-coordinate of -1. So it becomes 4 minus 2 times minus 1, which becomes 4 plus 2, or r equals 6. So that's actually the point which is furthest out from the center that we can go, because we said the furthest you can get is 6. All right, so we've made good progress. We've gotten our points. We need to now focus on our slopes. So we transition, talking about our slopes. And for that, we say, okay, we'll need to think about moving into parametric. So we're going to say x equals our r, so 4 minus 2 sine 1/3 theta times cosine theta, r cosine theta. Y is r times sine of theta. So let's see what happens. Remember, we need to look at y prime over x prime. So derivative of the first, well, derivative of 4 is 0. Then derivative of minus 2 times sine would be, well, derivative of sine is cosine. And then don't forget the factor of a third. So this would be minus 2/3 cosine of 1/3 theta. So that's derivative of the first times the second times sine, plus the first, 4 minus 2 sine of 1/3 theta, times the derivative of sine, which is cosine. Divide that by, okay, derivative of the first. Well, it's the same thing. Minus 2/3 cosine 1/3 theta times the second, cosine theta, plus the first, 4 minus 2 sine of 1/3 theta times the derivative of the second, minus sine theta. Good. Good. Now, we've got some great news. A lot of this we can simplify dramatically if we make a couple of simple observations. Notice that our angle is always going to be this angle coming up here. So, what's true about cosine and sine in our case? Well, cosine, if we're coming up the positive y-axis, is 0. So those terms are just going to completely go away. Sine is 1, because we're going straight up. And so, in our case, I'm not saying this is general, but for us, so for our case, emphasizing, it's not a true equality for all values of theta, but for the thetas that we care about, the terms with the cosine theta go away. We can ignore the sine thetas, and there's a minus here. Go ahead and cancel with that minus there. So we end up with 2/3 cosine of 1/3 theta over 4 minus 2 sine of 1/3 theta. So that's our slope. So, great, perfect. Now we just have to write down what happens at each one of our various angles. So, let's try it out. Now, by the way, this denominator, this is what we've called r. And we've actually computed r for all these terms. So we already know r. We just got to work on the numerator. And once we get that, life is good. Life will be wonderful. So, how about pi over 2? What do we get? Well, we're going to get a 2/3. And then here, we're going to get cosine of pi over 6. And then we're going to divide it by our value for r, which is 3. Now, do we know cosine of pi over 6? Yes, it's on the chart. Cosine of pi over 6, root 3 over 2. So, we have another root 3 over 2. So, that becomes 2/3 times root 3 over 2 times a 1/3. You can get some 2's to cancel. we end up with a root 3 over 9. All right, good. We did it. That's our slope. And notice, what does it say? It's a positive number, which is good because if we think about it, we said this should be at pi over 2, should be this one here. So it should be a positive slope. So that's a good sign. Now, we're going to run out of space here. Well, we probably can squeeze at least one more case in. Okay, so this is, again, this is our slope. Now, at 5 pi, not 3 pi, 5 pi over 2, well, it's a very similar setup, right? It's 2/3 cosine 5 pi over 6 all over 3. Now, the only difference is what's true about cosine of 5 pi over 6. If you think back to our picture, we drew it here. See, there's a relationship between pi over 6 and 5 pi over 6. The y values are the same. The x values have opposite sign, which means that when we talk about the cosine of pi over 6 versus the cosine of 5 pi over 6, they're negatives of one another. So the only difference between these two is a minus sign. So we get a minus root 3 over 9, and that's our slope. That leaves us with one angle left to talk about. And I guess I should pause and say, and see, it matches because it comes through, it should be a negative slope when we came through at 5 pi over 2. Our last one, though, 9 pi over 2. Okay, so 9 pi over 2, well, what do we have? We have cosine of 3 pi halves. So 2/3 cosine 3 pi halves divide by our value for r. Our value for r is 6, but it doesn't really matter. What's cosine of 3 pi halves? 0. So this term goes away. That's our slope. So it's flat. And that matches with our picture. It's a flat tangent line. Okay, so we have our points, we have our slopes, and now we're in great shape. Indeed, this is really easy to write down the lines because we have our slopes and our points are intercepts. So we'll start here. For pi over 2, our intercept is 3, and our slope is root 3/9. So we get y equals root 3/9 x plus 3. For the next one, 5 pi over 2, our intercept is still 3. Now our slope is negative root 3/9. So y equals negative root 3/9 x plus 3. For 9 pi over 2, our intercept is at 6. Our slope is 0. So y equals 0 times x plus 6. And that's it. Those are all our tangent lines to our curve, which hit the positive y-axis. And we're done. Wow. Okay, that took a bit, but it's nice to get an answer. Well, thanks for hanging in there. Hope you enjoyed it, and I hope you learned something along the way. Keep at it. Keep doing the work. The more that you do, the better you get. And I'll see you again in another session.